All right, let's talk about something we all kind of know, right? The universe has this hard and fast speed limit. You can't break it, and we call it c.
And if I asked you what C is, I bet you'd have an answer on the tip of your tongue. I mean, it's one of the most famous letters in all of science, isn't it?
The speed of light, of course. It's literally in the name. So you'd think, okay, to measure the speed of light, you need light. You'd probably shoot some photons and time them, something like that.
But what if we could measure this cosmic speed limit without using a single photon? What if we could do it just by watching how matter behaves? I'm talking about electrons. Yeah. Okay, you got to stick with me here because this is going to force us to totally rethink what C actually is.
So first things first, we got to get something straight. We need to stop thinking about light as being just about light. It's way, way bigger than that.
See, C is really what we should call the space-time constant. It's this fundamental property that's literally woven into the fabric of the universe. It's the top speed for everything, not just light. We're talking matter, energy, any kind of information. It's the ultimate speed limit on reality itself.
And a really cool way to think about this is something called the light speed curtain. Just picture this invisible wall at the absolute edge of what's possible. You can throw things at it, push them faster and faster, but if something has mass, it can never, ever break through that curtain.
Okay, so you're probably thinking, wait a minute, if electrons can't reach the speed of light, how on earth can they tell us what that speed is? And that is the perfect question. See, the secret isn't in reaching the limit, it's in how they act when they get really, really close.
You know, back in the old days of Newtonian physics, things were simple. You give something more oomph, more momentum, and its energy goes up in a nice, clean, straight line. But then Einstein came along and showed us the real picture. In reality, as you get an electron closer and closer to C, its energy just goes wild. The graph of its energy versus its momentum starts to curve up, like it's trying to climb a wall it can never get over, that light speed curtain.
And scientists have this awesome, kind of funny name for this bend in the graph. They call it the electron elbow. And believe me, this elbow is the whole key. The exact shape of that curve, that bend, is a direct giveaway. It's a signature of the space-time constant. So if you can just measure that elbow accurately, you can actually calculate the universe's speed limit.
And that, right there, brings us to this absolutely brilliant experiment. A setup designed to do exactly that, to measure the space-time constant using nothing but good old electrons.
So check this out. They call it the ratio method. Here's the basic idea. First, you fire electrons at different speeds. You do that by changing the voltage, and you shoot them through a crystal inside a microscope. When they pass through, they create this pattern of rings on a detector. So you measure the radius of those rings. You also have to measure a property of the microscope called camera length for each speed. But here's the genius part. The actual numbers don't have to be perfect. The whole calculation just depends on the ratios between these measurements. It's so clever.
And boom, this is what they see. This is the kind of pattern that pops up. Those faint circles, those are the diffraction rings from the electrons. And by measuring the tiny, tiny changes in how big those rings are when they crank up the electron's energy, they can actually trace out that electron elbow we were just talking about.
But, you know, this is science. It's never that easy. Just like in any good story, their beautiful, elegant idea immediately slammed into a huge real-world problem. A puzzle that, if they couldn't solve it, the whole thing was a bust.
So it turns out the entire experiment was ridiculously sensitive to one little thing. That camera length ratio we mentioned, which is kind of like the microscope zoom level. If that one number was off by just a tiny bit, their calculation for C would be, well, it'd be garbage. Totally wrong.
And guess what? That's exactly what happened at first. They tried using the standard, out-of-the-textbook values for their microscope's camera length, and the results were a mess. I mean, the paper literally says they were all over the map. The numbers for C they were getting were just chaotic nonsense. It really looked like the whole idea was a failure.
But this is where the real genius kicks in. This is what science is all about. They flipped the script. They turned the problem into the solution. They basically said, okay, forget the textbook value, let's just ask the data. What number for that camera length ratio would we need for all our measurements to actually agree with each other? They let the experiment find its own sweet spot.
And the second they did that, it was magic. The chaos just disappeared. All their different data points suddenly snapped right into place, all huddled together right around the actual known value of C. It worked. They had actually done it. They measured the cosmic speed limit just by looking at electrons.
So, okay, they did it. But what does this all mean?
What are the bigger takeaways from this incredible experiment?
Well, the number they got was about 3.0 times 10 to the 8th meters per second. Now look, there's about a 20% uncertainty there, so it's not going to win any awards for being the most precise measurement ever. But that was never the point. The real victory here was proving that the method works, that it's even possible to do this.
And this is not just some cool party trick for physicists. It actually has a super practical use. It can be used as a metrology check. Basically, it's a simple, clever way for any lab with an electron microscope to double-check its own settings and make sure it's calibrated perfectly, just by using the fundamental laws of the universe. How cool is that? So, when you boil it all down, the takeaways are huge. First, this is beautiful proof that c really is a property of spacetime, not just some random speed for light. Second, it shows you don't always need a giant billion-dollar machine to test fundamental physics. Sometimes a clever tabletop experiment is all you need. And finally, it proves that everything in the universe, whether it's a particle with mass like an electron or one without, like a photon, they all have to play by the same cosmic rules.
And that just leaves you with this one last, kind of mind-bending thought, doesn't it? This entire discovery came from just looking at a plain old electron in a new way. So if an electron is holding a key to the secrets of spacetime, it really makes you wonder, what other massive, universe-changing secrets are just hiding out there in plain sight, just waiting for someone to ask the right question?